let's get going. Welcome back. This is the 11th lecture of the condensed matter course. Where we left off last time, we were studying reciprocal space. Reciprocal space. And we came to this understanding that the reciprocal lattice is somehow the Fourier transform of the direct lattice. And the reason we want to study reciprocal space is because it's going to make our life easier when we come to studying waves. So it's a rather important thing to understand well. And sometimes it's hard to understand Fourier transforms well because they're not something that we think about in everyday life. It's a little bit complicated. So it turns out that there's a much nicer geometric way to understand a lot of reciprocal space, which is what we're going to discuss today. So I need some definitions as usual. Let's start with a simple definition. A lattice plane equals a plane containing three non-collinear and therefore linear and therefore an infinite number and therefore for an infinity of lattice points. Okay, so a lattice plane is a plane containing three non-collinear and therefore an infinite number of lattice points. So here's some pictures of lattice planes. Here on the left we have a BCC lattice. There's a plane cutting through 3 points. Therefore, if you continue it out to infinity, it will cut through an infinity number of points. That's a lattice plane. On the right is a simple cubic lattice. There's a plane that cuts through 3 lattice points. If you continue it out to infinity, it cuts through an infinite number of lattice points. Another definition, a family of lattice planes. Mama lattice plane, baby lattice plane. No, I'm joking. That's not what no one ever laughs in this class. I don't get it. Family of lattice planes equals an infinite set of equal spaced lattice planes such that all lat points are included in one of the planes. Let me know if my writing starts getting to be too messy to read. So here's a simple cubic lattice and a couple of families of lattice planes. Each one of these is a lattice plane that cut through an infinite number of lattice points, and they're equally spaced, and they include every single point in the lattice when taken all together. This is a BCC lattice, and there's a family of lattice planes for the BCC lattice, cuts through all the lattice points in the BCC lattice. This, however, is not a family of lattice planes for the BCC lattice, even though they're lattice planes, what's drawn. They are equally spaced, but they do not include every lattice point. They miss these guys here in the middle of the conventionally unit cell. Therefore, it is not a family of lattice planes. Okay, so the connection to the reciprocal lattice. Claim. A family of lattice planes is perpendicular to a reciprocal lattice vector which I'll call G, and further, and the distance, the spacing between neighbor planes is d equals 2 pi over absolute G min, where G min equals shortest lattice vector, lat vec in direction of G. Okay, this is an important statement. Every time we have a family of lattice planes, orthogonal to this family of lattice planes, there is a reciprocal lattice vector. And if you want to know the spacing between the lattice planes in the family of lattice planes, you find the shortest reciprocal lattice vector pointing in that direction. 2 pi over the absolute value of that shortest reciprocal lattice vector gives you the spacing between planes. Okay, this is a big statement. We haven't shown it. It's useful to actually prove this statement because actually in the proof there's a lot of important geometry that we're going to need in coming up in a moment. So let's go through the proof that this is true. So first of all, so this is just a proof by geometry. So a little bit of geometry that you probably remember. First of all, let's define a plane. Pick our vector g. G dot point x equals a constant c. Defines a plane of points x. Perpendicular to G, where, okay, let me actually draw this over here. So here's the point 0, here's the vector G, here's the plane perpendicular to G, which we're calling x. This is the plane of points x. And the distance from 0 to the plane x, let's call that distance x min, here, where x min, the minimum distance to the plane, equals c over absolute G. Okay, does that geometry look familiar from before? Does it look reasonable? Yeah? So the x min here is c over absolute G if we're defining the plane by g dot x equals c. Okay, so that's how we're going to define a plane. Now we're going to define a set of planes. We define by e to the I g dot x equals 1. So why does that define a set of planes? Well, e to the I g dot x equals 1 is the same thing as saying g dot x equals 2 pi m, where m is an integer. M is an element of integers, right? So that means we have a whole bunch of planes whose minimum distance to the origin is given by 2 pi m. So x min equals 2 pi m over absolute G. So spacing between these planes, spacing between planes d is 2 pi over absolute G. Okay, let's actually, I have a better picture of that than I can draw. So the geometry we're interested in is e to the I g dot x equals 1. It defines a set of parallel planes. One of the planes will be g dot x equals 2 pi m. Another plane will be g dot x equals 2 pi m plus 1. The distance to the first plane is 2 pi m over absolute G. The second distance to the second plane is 2 pi m plus 1 over absolute G. So the distance between the two is 2 pi over G. Does that geometry look pretty good? Yeah? Okay, good. All right. So now recall that if G is a reciprocal lattice vector, so G is a reciprocal lattice vector, lat vec, then e to the I g dot r equals 1 for all r in direct lattice, That's our definition of the reciprocal lattice. So what that tells us is that every lattice point is going to be included inside this set of planes. Okay? Because any r will have to satisfy e to the I g dot r equals 1 if G is a reciprocal lattice vector. So all of our lattice points in the direct lattice are going to be included in this set of planes that we just defined. However, it does not mean that every plane cuts through lattice points. Okay? Why not? Okay, here's a picture to explain that. Here we have a set of planes defined by some reciprocal lattice vector, which I'll happen to call G min. And here we have a set of planes defined by twice that reciprocal lattice vector. The spacing between the lattice planes is half as big, because the spacing is always 2 pi over g. You'll notice that in the second picture, we have a plane which is defined by this reciprocal lattice vector g, which doesn't intersect any lattice points. What we're guaranteed by this law is that all direct lattice points must be included in one of the planes, but we're not guaranteed that every plane has to cut through a lattice point. Okay? So if we want to get a set of planes in which every plane cuts through the lattice points, we have to choose. So to get family of lattice planes, and to be a lattice plane, it has to cut through a lattice point. So if we want a set of planes where every plane cuts through a lattice point, we must choose G min, the shortest reciprocal lattice vector in that given direction. If it was not the minimum reciprocal lattice vector in that direction, you could make it smaller, cut it in half, for example, and get something which has fewer planes, and yet all of the lattice points should still be included. So you should take the minimum reciprocal lattice vector so that you get enough planes. You're guaranteed that all your lattice points in the direct lattice will be included in those planes, but you don't get any extra. Okay? Good. All right, so that's the proof of that rather important theorem. Now it's useful to actually come up with some way to describe these reciprocal lattice planes, or these family of lattice planes, or these reciprocal lattice vectors. And this is a type of notation that we will use very frequently, known as Miller indices, for describing families of planes, or vectors in reciprocal space, vectors in recip space. And the idea of a Miller index is that you write in parentheses HKL to mean, actually maybe I'll, before I do that, I'll write, we describe families of planes or vectors in reciprocal space in terms of reference vectors, reference vex B sub I. These B sub i's, very important, they may be primitive reciprocal lattice vectors, or they may not be. Generally, what we do is we write, this was I was starting to write a second ago, HKL in parentheses to mean H times B1 plus K times B2 plus L times B3. And this notation should look a little bit familiar. We can compare it to the notation we used in real space, in direct space. Direct space, we use the notation U, V, W to mean U times A1 plus V times A2 plus W times A3. So the important thing to take away here is that if we use curved parentheses here, we mean reciprocal space. If we use square brackets, we mean direct space. So don't confuse those with each other. Now, in both cases, we may or may not mean these A's or these B's to be primitive. Okay? That's very important, because a lot of the questions that come up on exams exactly reference this subtlety, that sometimes you work with primitive reciprocal lattice vectors or primitive lattice vectors, and sometimes you don't. Why don't you sometimes? Because sometimes the primitive lattice vectors or primitive reciprocal lattice vectors are at ugly angles, and if you choose to use a conventional unit cell rather than a primitive unit cell, you can use orthogonal vectors rather than using things at weird angles. So if you can use orthogonal, you usually do, even if it means you're not using primitive lattice vectors. Okay? So let's be careful here, being careful about our definitions. The rules kind of go like this. First, choose direct real space vectors, direct space vectors A sub I. That's going to be these things, which may or may not be primitive. I'll even write that down. May or may not be PLVs. PLVs. Now for us, you'll remember we had this rule that we're not going to be responsible for lattices in 3 dimensions where the axes are not orthogonal. Okay? For us in 3D, we always choose orthogonal A's. Okay? Sometimes in 2D they'll ask a question where they're not orthogonal, but in 3D we always choose orthogonal A's. That means for simple cubic, these are primitive lattice vectors, PLVs, but for FCC and BCC, these are not PLVs. But they have the advantage of being orthogonal, so they make your life a lot easier because it's a lot easier to work with things that are orthogonal than things that are not orthogonal. Okay? So given that we've defined these A's, we then construct B's. So call that 2. Construct B's by bi.aj equals 2 pi delta ij. And we've seen this equation before. If and only if A's are PLVs, then B's will be reciprocal PLVs, our reciprocal lat PLVs, primitive lattice vectors. Okay? Again, for us, since we are using in 3D, since we are always using orthogonal axes in 3D, it will always turn out to be the case that the absolute value of BI equals 2 pi over the absolute value of AI because axes are orthogonal. Axes orthogonal. Okay? So that makes life a lot easier. So generally, when we write down G equals HKL, we mean, where is it? This thing over here. HB1 plus K, and I'll write it again. We mean HB1 plus K, B2 plus L, B3, where the B's have been constructed in this way. But always G defines a set of planes, a set of planes via e to the I g dot x equals 1. E to the I g dot x equals 1. So we can always define a set of planes from any vector g via e to the I g dot x equals 1. And the spacing of these planes, is d HKL equals 2 pi over absolute g, or I guess in assuming orthogonal axes, assume orthogonal, B's orthogonal, or A's orthogonal, A's and B's orthogonal, or orthogonal. Then we can write that as 2 pi over absolute value of h squared absolute b1 squared plus k squared absolute b2 squared plus L squared absolute b3 squared. Okay. And for cubic lattice, for cubic, where A1, A2, and A3 are the same length and orthogonal to each other, therefore B1, B2, B3 are the same length and are orthogonal to each other, the spacing d HKL is A, the length of the the length of the conventional unit cell in direct space over h squared plus k squared plus L squared. Okay? And maybe I'll note this one more time. If the A's are PLVs, then the B's are PLVs, then B's PLVs. Did I write that above? B's PLVs. And that means that HKL is a reciprocal lattice vector, recip lat vec. But it's not always the case if the A's are not PLVs to start with. Okay? All right. So supposing someone hands you a set of planes and asks you for the Miller indices, that sounds like it might be hard to figure out, but in fact, there's an easy way to figure out geometrically what the Miller indices are for a set of planes. And this is known as the method of intercepts. Method of intercepts. Goes kind of like this. So suppose we have, so here's three axes, x-axis, the y-axis, and the z-axis. Let's assume orthorhombic, so the primitive lattice vectors in the three directions aren't necessarily the same. So let's call this A2 and 2A2. And this one will be, I guess, A1, 2A1, 3A1, maybe 4A1 here. And then A3, 2A3, and 3A3. So suppose that we have a plane going through the origin. So imagine there's a plane cutting through the origin here. And then also cuts through the axes like this. Okay? So you take the first two parallel planes. One of them cuts through the origin. It's parallel to this plane, which cuts through the axes like this. The rule is that HKL, maybe I'll write it this way, H is to K is to L as a proportionality is the same as A1 over the x-intercept is to A2 over the y-intercept is to A3 over the z-intercept. So in this picture here, this would be A1 over the x-intercept is 1 over 4. A2 is over the y-intercept is 1 over 2. And A3 over the z-intercept is 1 over 3. So it should have the same ratios as this. If we multiply by the least common multiple, we get 3, 6, 4 as Miller indices that would be appropriate for this plane. And generally you write it as 3, 6, 4 without any commas, at least as long as there's no confusion as to where you should put the commas. If you go over 10, then you have to indicate where the commas are. Otherwise, it's not clear where it would be. All right. Now, and what we mean by 3, 6, 4 here is that 3, 6, 4 is 3 B1 plus 6 B2 plus 4 B3, and that's what we mean by the Miller indices. And that set of Miller indices gives a reciprocal lattice vector which is normal to this plane. There's some cases which are a little more complicated. If a plane does not intersect an axis, intersect an axis, then you get a Miller index of 0. You get Miller index equals 0. Let's see if we can explain why that is. So here, again, three axes. This is the A1 axis out here. Maybe this will be A2. This will be 2A2. And maybe here we have 3A3. And suppose we have an axis always a plane always cutting through 0, and then the next plane cuts here, but it's parallel to the A1 axis here, to the x-axis, so it never intercepts it. So what do we do with the Miller indices? Well, we say H is to K is to L as, well, okay, so the first question is where do we intercept the x-axis? Well, if it doesn't intercept the x-axis at all, you can say that it's really like intersecting the x-axis at infinity. So we write 1 over infinity here. And then K, well, we intersect the y-axis at 2, so 1 over 2. And we intersect the z-axis at 3, so we write 1 over 3. And multiply by the least common multiple, and we get 1 over infinity is 0, 3, 3, 2. So the Miller indices here would be 0, 3, 2. Okay? So let me show you a couple examples of this. Here's a set of Miller indices that are 1, 0, 0 because it intersects x at 1 and doesn't intersect z or y. Here's one that's 1, 1, 2 because it intersects x at 1, y at 1, and z at 1/2. The reciprocal of 1/2 is 2, so it's 1, 1, 2. So you can have a situation, can have Miller index less than 0, index negative, like 1, minus 1, 0, which you typically write as 1 with a bar over it, 0. Okay, so the bar means negative. That's just the notation that's conventionally used. Now, okay, so here is a great big apology for the uncoordination of our community. So depending on which side of the ocean you come from, the way you say this out loud is different. If you're from the United States, you say 1 bar 0. If you're from England, you say 1 bar 1 0. I don't know why. It makes things incredibly confusing. When it's written, it's totally unambiguous. The bar on top means negative. But when you say it out loud, it's totally confusing and no one knows what you mean. So I recommend just writing it down and then everyone knows what you're talking about. Okay, let me show you an example where we have a negative Miller index. So this plane here, actually maybe it's not so clear, but you're supposed to sort of be able to extrapolate down with your eyes and see that this plane sort of starts up here and goes down and it would intersect the z-axis at minus 1/2. And so its intercepts are 1, 1, minus 1/2, so its Miller indices are 1, 1, 2 with the bar over it. Negative 2. Okay? So here's a whole bunch of different Miller indices for bunches of different planes. 0, 0, 1, 1, 0, 0, 0, 1, 0, 1, 0, 1, so forth and so on. And you see that they actually kind of come in families. So if you look at the family across the top row, you'll see that 0, 0, 1 and 1, 0, 0, they kind of look similar, and 0, 1, 0 looks kind of similar. And if you imagined actually having a sample, as a simple cubic lattice, and you picked up the simple cubic lattice and you looked at it from one side, 1, 0, 0 would look exactly like 0, 1, 0, depending on if you picked it up and turned it sideways. It's exactly the same. It just depends on which side you picked up and looked at first. Similarly with 1, 0, 1 or 1, 1, 0, if you picked it up and you looked at it sideways, it would look exactly the same. Okay? The spacing between planes in those families would be exactly the same. The way it cuts diagonally through the unit cell would look the same. It just matters which way you picked it up in the first place. So we have a notation for equivalent sets of Miller indices. Equivalent sets of Miller indices, which we notate with curly brackets. Okay, that was a terrible curly bracket. Like that, HKL, which means equivalent sets of HKL in regular parentheses brackets. So for example, in this picture, curly brackets 1, 0, 0 would mean 1, 0, 0 or 0, 1, 0 or 0, 0, 1 or 1 bar 0, 0 or 0, 1 bar 0 or 0, 0, 1 bar. Uncoincidentally, these planes look like the surface of a cube, and you can pick up the surface of a cube and look at it 6 different ways, and it would look equivalent from all of those 6 different angles. We also have what's known as the multiplicity of HKL, which is the number equals the number of parentheses HKL in bracket HKL. So in this case, we would have multiplicity of 1, 0, 0 is 6, because it includes all those 6 different sets of Miller indices that I wrote down. Okay? So, for the first candy bar of the day, what is the multiplicity of 1, 2, 3? No.
Well, 6.
No. What was it? Someone said something? 48. Yeah. Who said that? 48. This one's yours. Very good. I can't throw it that far. 48. The answer is 48. So let's see why the multiplicity of this is 48. First of all, 1, 2, and 3 can be in any order. So that's 3 factorial, gives you 6. 1, 2, 3, 1, 3, 2, 2, 3, 1, 2, 1, 3, 3, 1, 2, 3, 2, 1. 6 possible ways of ordering them. But then in addition, any one of those numbers can have a bar over it or not. So if this one has 2 possibilities, this has 2 possibilities, this has 2 possibilities, that makes 8 possibilities. So it's 8 times 6 gives you 48. Okay? So multiplicity of 1, 2, 3 equals 48. Which is kind of interesting. It means if you have the family of lattice planes associated with the 1, 2, 3 Miller indices, you can pick up a simple cubic lattice and look at it from 48 different directions and have lattice planes with exactly the same spacings looking at you. Okay? Sort of surprising, but that's true. Okay, so now why is it we care so much about these lattice planes, besides the fact that they're going to tell us a lot about reciprocal space, and we're interested in waves, and waves, reciprocal space is a language of waves. Well, one reason we might be interested in these families of lattice planes and reciprocal space is because they actually tell you a lot about the macroscopic structure of the crystal. It's kind of interesting that all of this information about lattice planes and reciprocal lattices, this was all worked out in the middle of the 1800s before people even knew that there was such thing as atoms. And the way it was worked out is because people knew that minerals, nice crystalline minerals, broke, and so they fractured only along certain axes. And that enabled them to deduce all of this information. So for example, with a simple cubic lattice, you'll discover, or any type of cubic lattice, that the lattice will break, the material will break along simple sets of Miller indices. So like the 1, 0, 0 face here, or the 0, 1, 0 face here, is where the material will break most easily. This is a law. It's not a hard and fast law, but it's a very, very good rule of thumb by Bravais, known as Bravais' law, the same guy who worked out all the lattices. And it actually tells you that when you take a cubic crystal and you break it, you get only the 1, 0, 0 faces. Occasionally you'll get the 1, 1, 0 faces, and even less occasionally you'll get 1, 1, 2. So here's a picture of sodium chloride, which is a cubic crystal. It's actually FCC crystal. And it breaks almost exclusively along the 1, 0, 0 lattice planes. You can see that these breaks are entirely at 90 degrees. Quartz, okay, we don't study quartz this year. It's just a very nice picture, so I put it in there. We don't study it this year because the axes are not orthogonal to each other. It's a trigonal crystal. But the axes very clearly, the faces are very clearly at very fixed angles to each other, which are dictated by how the lattice planes are arranged. Okay, so I'm going to emphasize this one fact one more time because it shows up on exams so frequently. So this is important fact. If A's are PLVs, then if and only if A's are PLVs, then B's are PLVs. I think I've written this down 3 times today. Then B's are PLV, maybe reciprocal PLVs. For example, this is true for simple cubic, which means any HKL is HB1 plus K B2. This is the definition of HKL, B3. So any of these is a recip lattice vector. Recip lat vec, because integer sums of primitive lattice vectors give you an element of the lattice. If we want a family of lattice planes, of lat planes, we should be shortest in a given direction. Shortest recip lat vec in a given direction. So for example, if we're considering the direction 2, 4, 6, the shortest reciprocal lattice for the simple cubic lattice, the shortest reciprocal lattice vector in that direction is 1, 2, 3. So you divide by greatest common divisor. So if you want to describe a set of lattice planes, you should always choose the reciprocal lattice vector which is shortest in that given direction. However, if the A's are not PLVs, then the B's are not PLVs, not recip PLVs, which means that not all HKL are recip lattice vectors, And this is the source of most good exam problems. Okay, so let me show you exactly what we mean by this. So recall this picture. The lattice planes the family of lattice planes I've drawn in this picture here is the 1, 0, 0 family of lattice planes, and G, the minimum reciprocal lattice vector in that direction, is in fact 1, 0, 0. This is simple cubic lattice, so this is definitely a family of lattice planes and a reciprocal lattice vector. Now, twice that, 2, 0, 0, is a reciprocal lattice vector, but it's not a family of lattice planes because you have extra planes. You have a plane that doesn't cut through any lattice points, half the spacing of planes. So it's not a family of lattice planes, but it is a reciprocal lattice vector. Now let's think about what happens when we go to either a BCC or an FCC lattice. With a BCC and an FCC lattice, we're still going to use the same 3 orthogonal A's. We're going to choose to use the conventional unit cell to define our A's, just like we did with a simple cubic lattice. And we're doing this, they're not primitive lattice vectors, and that's a problem, but we're doing it because we want to keep everything orthogonal, and life is just a lot easier if you keep everything orthogonal. Okay, so here's a picture with a bunch of Miller indices and a bunch of lattice planes drawn for the simple cubic lattice. Here's the 1, 0, 0 set of lattice planes, just like I drew before. Now in the BCC case, if you added one more point in the center of that unit cell, in the center of that conventional unit cell, it would not be intersected by the 1, 0, 0 set of planes. It is intersected by the 2, 0, 0 set of planes. So 2, 0, 0 is a correct family of lattice planes for BCC. It is not for simple cubic. Okay? 1, 0, 0 isn't even a reciprocal lattice vector for BCC because it does not intersect every lattice point. Okay? That's the subtlety, and we're going to come back to this subtlety over and over. For a BCC, you have to choose Miller indices to make sure that every one of your lattice points is included in one of those planes. Same for FCC. And the reason this is a problem is because we're using lattice vectors A, which are not the primitive lattice vectors. We're using orthogonal vectors because orthogonal makes your life easier, believe it or not. Same with FCC. If we consider the FCC lattice and you consider the 1, 1, 1 planes, these planes here, we would not intersect some of these lattice points. These would be missing. So 1, 0, 0 is not a reciprocal lattice vector for FCC. 2, 0, 0 is. Okay? Similarly, well, we can look at 1, 1, 1 here. So 1, 1, 1 is a perfectly good a family of lattice planes for simple cubic. It would not be a family of lattice planes for BCC because it would miss the point in the center of the unit cell, but actually it is a family of lattice planes for FCC because it just happens to catch all of those points in the center of the faces. Okay? Now later on we're actually going to derive a condition which will tell us when we have Miller indices which are a family of lattice planes for a particular lattice. But it's important to realize not every set of Miller indices will give you a reciprocal lattice vector or a family of lattice planes for BCC and FCC lattice. And the origin of this problem is we're not using primitive lattice vectors to describe our conventional unit cell. We're using the edges of the conventional unit cell. Okay, is that clear? Have I warned you enough? All right, good. All right, so that's everything we have to say about reciprocal space. And now we can get on to some applications of reciprocal space. And perhaps the most important application we're going to run into is scattering experiments. Scattering experiments, which will be the subject of the rest of this lecture and probably much of the next 2 lectures. So the general scattering experiment starts with a sample. You send in some wave with wave vector k. Some of it goes through unscattered, comes out at wave vector k, and some of it comes out at wave vector k prime. By observing what comes out at wave vector k prime, you're supposed to be able to deduce what is in the sample. Now, it's hard to overstate the importance of this type of experiment. You may have studied it in other courses, especially subatomic, but it is not an overstatement to say that almost everything we know about the microscopic world, everything, the fact that we know that there are nuclei, the fact that we know the structure of atoms, the fact that we know the structure of materials, the fact that we know the structure of the proton, all of these things come from this kind of experiment, this type of scattering experiment. You know, we grew up in a world where even kids know what atoms look like, and they know what DNA looks like, this double-stranded helix. They know what water molecule looks like. They may even know what salt looks like, sodium, chlorine, sodium, chlorine. All of this stuff that we know and we take for granted comes from doing this kind of experiment. The only thing that's different when we do this experiment versus when the high-energy physicist is doing this experiment is what wave we put in to start with. Okay? Now, we're interested in seeing atoms, and atoms are on the scale of about an angstrom. It turns out to be a really good idea to choose a wave whose wavelength is about the same scale of the thing you want to see. So for us, there are going to be a couple of options. One is X-rays, electromagnetic waves, whose length scale is about an angstrom. So that will enable us to see things roughly of the size of an angstrom. But, you know, we live in this quantum mechanical world, and we know that waves and particles are the same thing. So we're entitled to use not only things we usually think of as waves, but things we usually think of as particles. So a particle, which is very convenient to do scattering experiments with, is neutrons. Neutrons, you know, think of them as particles, but they're also waves. It turns out to be fairly easy to get neutrons to have wavelengths which are on about the same scale of about an angstrom, which makes it easy to see things which are on the scale of roughly an angstrom. These are pretty much the two types of waves that we're going to be responsible for this year. I should mention that people frequently use electron waves as well, but we don't study them this year because they have some complications which we don't want to delve into. So whatever type of wave we send into our material, the thing that we're supposed to imagine is that the atoms in the sample provide a potential V of r that scatters the wave. And our objective is actually a bit of an inverse problem, where instead of trying to calculate what does the potential do to the wave, much more frequently we're told what the wave has done. We've measured what the wave has done, and we're trying to deduce the potential. The potential is going to tell us where the atoms are in the material, and we're trying to deduce that from observing what physically came out of our sample. Now, just a little bit of a caveat. It's easy to think about a potential for neutrons. A neutron moves around, it feels some potential as it moves around. It's a little bit less natural to think about a potential for X-rays, which are electromagnetic waves. You can, if you want, you can kind of think of it as a potential for photons, but much more appropriate is you really should be thinking of it as spatially dependent optical index or spatially dependent dielectric constant. But you won't go too far wrong to think about it as just a potential for particles as a particle move through your material. So the way we're going to actually calculate how much gets scattered out at some wave vector k prime is to use Fermi's golden rule. Fermi's golden rule. Condensed matter joke. You know, this is a symbol for gold. Anyway, never mind. So I made that up on the spot. It was because I was trying to save my arm from writing. All right, never mind. I'm not going to be a comedian. That's why I'm a physicist. Okay, so the scattering rate from k to k prime is given by, you'll probably seen Fermi's golden rule, 2 pi over h bar. There's a matrix element, k prime v k, that gets squared, and an energy-preserving delta function. These are vectors. Energy-preserving delta function. Now, to simplify our life, we assume elastic scattering. Elastic scatter, which means that E equals E prime. The energy coming in and the energy coming out are the same. That will also mean the absolute value of k equals the absolute value of k prime. There's several reasons why we assume elastic scattering. First of all, it's easier. Secondly, and when you actually do these experiments, most of the scattering that you measure actually is elastic. It's actually quite interesting to look at inelastic scattering as well. I might mention that a couple of lectures further on. With inelastic scattering, you leave some energy behind in the sample, and that actually allows you to figure out what the energy of the possible excitations are that you can excite in the sample as well. But that's a little bit more complicated, so we're not going to worry about that for now. So we're just going to assume elastic scattering. And the only thing that's difficult in that expression, Fermi's golden rule, is the matrix element. So let's write out the matrix element. So we have k prime v k equals what? Well, we'll use the real space representation of these kets. It's integral dr of e to the, let's see, signs, e to the I k prime dot r times v of r times e to the I k dot r. Do I have the signs right? Yeah, okay. And if you were careful, we would normalize this by 1 over square roots of volumes. This is the wave vector. This is the wave function k prime. This is the wave function k. There's v of r in the middle. And we realize that what that is, well, we'll write it this way. d3r e to the minus I k prime minus k dotted with r, v of r. That is just, well, we'll write it as v twiddle of k minus k prime, where v twiddle means Fourier transform. V twiddle equals Fourier transform of v of r. This is a very, very general rule that the scattering amplitude from k to k prime is just the Fourier transform of the scattering potential. Now, in the last lecture, so that actually almost always holds true for anything that you're going to do scattering experiments on, that the scattering, using Fermi's golden rule, the scattering amplitude from some k to k prime is just the Fourier transform of whatever the scattering potential is. Now, in the last lecture, we considered Fourier transforms of periodic functions. So we're going to assume we have a crystal, assume a periodic scattering potential, v of r. So if we have anything that's crystalline, the potential will be periodic. And so we can use the law that we derived in the last lecture, that the Fourier transform of a periodic potential, k minus k prime, equals a sum over reciprocal lattice vectors g of a delta function, three-dimensional delta function, of k minus k prime, write that again, k minus k prime minus g times the structure factor of g. I guess there's some normalization factor, 2 pi cubed over the volume of the unit cell, and the structure factor here, s of g, running out of space, s of g equals the integral is equal to the Fourier transform within a unit cell, integral d3r e to the I g dot r of v of r. Write the r's the same way. And it's integral over the unit cell. Okay, a couple of important, so this is a law that we derived last time. And a couple of important facts about this law that we mentioned last time. First of all, the Fourier transform of this periodic function is 0 unless we're looking at values of k which are elements of the reciprocal lattice vector. So, point 1, scattering is 0 unless k minus k prime is a reciprocal lattice vector g. This is important. Put a box around it. This is known as the Laue condition, after Max von Laue, who won a Nobel Prize for discovering this in X-ray scattering. His Nobel Prize was actually exactly 100 years ago now. And then there's this complication about whether it should be called the Laue condition or the von Laue condition, because he was born Max Laue, but then his father was elevated to noblehood much later, and he took the name von Laue. But when he discovered this, his name was still Laue, so it's usually called the Laue condition, not the von Laue condition. But other people will disagree. So anyway, it's either the Laue condition or the von Laue condition. But we've seen this thing before. What this is conservation of crystal momentum. You only scatter if you can conserve crystal momentum. Right? If k minus k prime is a reciprocal lattice vector, that conserves crystal momentum. It doesn't change the crystal momentum of the wave. The second important fact that we're going to use later is that the intensity of scatter is the structure factor S of, delta k squared, where delta k is the reciprocal lattice vector G, which you've scattered by. Okay? So the point is that if you measure the intensity of the various scatterings, you can figure out the structure factor. What you're measuring is the structure factor at given reciprocal lattice vectors. The structure factor of given reciprocal lattice vectors is the Fourier transform of the scattering potential. So in principle, you're measuring the scattering potential. That's the point. By measuring what is scattered, you're actually measuring the scattering potential. Now, I'm sorry, I'm going to go over about 1 minute here. It may seem a little bit surprising, this condition 1, that you only get scattering under certain conditions. Only if crystal momentum is satisfied. Only if you satisfy this Laue condition. Now that might seem a little bit weird, but I'm going to convince you that this is something that you know very well. So imagine you have a crystal like this. Then you think of, really this is a bunch of lattice planes. It's a family of lattice planes. And you send some wave into a family of lattice planes, and it bounces off, but it could bounce off this layer too. And you know very well that if you bounce off planes like this, you can get diffraction, and diffraction only occurs at certain angles. You only get constructive interference at certain angles. And what we're going to see is that this Laue condition is actually exactly the same condition as having constructive interference. And we'll do that next time. I'll see you Wednesday.